Back, everyone, to the weekly fractional calculus seminar series. Today's speaker is Professor Alexander Meskhi. He is president of the Georgian Mathematical Union since 2022. In 2024, he was elected as a member of the Georgian National Academy of Sciences. In 1998, he defended his PhD thesis, and in 2001, he got the degree of Doctor of Science. In 2003 to 5, he was postdoc at the Scuola Normale Superiore of Pisa. Alexander Meskhi was awarded by Euler Premium for Young Scientists, established by the German Mathematical Association, 2000, Award of the Georgian Mathematical Union for the Best Scientific Works, 2002 and 2009, Andrea Razmadze Prize of the Georgian National Academy of Sciences, 2012. In 2017 to 22, he was a scholar of the Georgian National Academy of Sciences. Since 2022, he is chair of the organizing committee of the annual International Conference of the Georgian Mathematical Union, held in Batumi, Georgia. Alexander Meskhi is editor-in-chief of the Transactions of A. Razmadze Mathematical Institute. He is head of Department of Mathematical Analysis at A. Razmadze Mathematical Institute of I. Javakishvili Tbilisi State University and professor at Kutaisi International University. Since 2016, he is an invited professor at San Diego State University, Georgian branch. He is an author or co-author of 7 monographs and about 150 scientific papers. He was supervisor of 6 PhD theses. And today he is going to speak to us about the trace inequality criteria for fractional integrals. Please, the floor is yours.
Yeah, thank you very much for your introduction. And so the title of my talk, it is Trace Inequality Criteria for Fractional Integrals. Okay, so my talk consists of 3 parts. In part 1, we will discuss trace inequality for Riesz potentials and one-sided potentials. So it is splitted. First, we will discuss Riesz type potentials, and at the end of my talk, one-sided potentials. But in the middle, we will discuss boundedness criteria for fractional integrals defined with respect to a general measure, and one of the part, it is devoted to the sharp-weighted estimates for the norms or Riesz potentials. In particular, we will discuss Sharp-Olsen's inequality. So we will deal with both linear and multilinear fractional integrals. First part, trace inequality for Riesz potentials. So Riesz potentials given by this formula defined on Rn play important role in harmonic analysis and partial differential equations. For example, it is well known its importance in the theory of Sobolev embeddings. This theory, it is very well delivered in the monographs by Mazia or Adams and Hedberg, well-known monographs. So now what is a trace inequality? Trace inequality for Riesz potential I alpha, it is the inequality of this form where nu here, nu on the left-hand side, nu is a Borel measure defined on Rn. So, and on the right-hand side, we have the back measure, and this inequality, it is in the literature is known as a trace inequality. So to solve the trace problem, it means to characterize completely measure nu for which this inequality holds. So this is the trace inequality in Lebesgue spaces. So this inequality has a quite long history. In 1971, David Adams characterized completely this inequality in the case when P is strictly less than Q. And in this case, he proved that the necessary and sufficient condition for this inequality 0,2 is the following condition, that there exists a constant C such that for all balls in Rn, this inequality holds. So for us, it will be useful to introduce a characteristic of measure nu given by such a formula, by this symbol we denote supremum with respect to all balls B, nu B, 1 over Q, the volume of B, alpha over N minus 1 over P. So nu is absolutely continuous with respect to Lebesgue measure. So if, for example, that D nu, it is v of x dx, where v is a weight function. Weight function means that it is almost everywhere positive locally integrable function on Rn. Then the weight characteristic of V, it is denoted by this symbol here. So here nu, measure nu, it is replaced by V. V of B means that integral on B from V. Okay, so we need these two characteristics here. Okay, so regarding the trace inequality criteria, there exist several different characterization of the trace inequality. For example, and I list those by Mazia, Verbitsky, Adams, Hedberg. They have characterization of the way of the trace inequality in terms of capacities. And this characterization involves the most important case, P is equal to Q. This is called diagonal case. There exists Mazia-Verbitsky characterization of the trace inequality. Again, in the case P is equal Q, this is called, this condition, it is called pointwise condition, which involves risk potential I alpha itself. And there exists also Sawyer type of characterization, again involving the diagonal case PQ and Sawyer type condition. I can tell that this condition, it is again not transparent condition, contains the operator I alpha itself. Okay, trace inequality, it is a special case of the two-weight inequality. What is the two-weight inequality? So let's now, on the right-hand side, is instead of dx, let's write wx dx. W, it is a weighted function. Nu, we have on the left-hand side measure nu, Borel measure nu. So to solve that two-weight problem, this means just to give a characterize completely. Just a moment. Let me. I would like to write also something. Just a moment. I have here. Okay, but that's okay. I can explain without writing. So to solve the two-weight problem means that to find necessary and sufficient condition on the couple nu W, which guarantee this inequality. Okay. About a few words about the history of the two-weight problem. There exists Sawyer characterization of the two-weight inequality, Sawyer type condition. Again, it consists of two independent conditions involving operator I alpha, its potential operator I alpha itself. This case deals with so involves also diagonal case P is equal Q, and there exists transparent integral type condition due to Gabizashvili-Kokelashvili. In the literature, they are known. This condition, it is known as condition Gabizashvili-Kokelashvili. In fact, then it consists of two independent integral type conditions, but in this case, it is for the case when P is strictly less than Q. So, for example, about the latter condition can be found in the monograph by Kokulashvili-Kpes of 92 or 93, I think 93. Okay. What is one of our aims? One of our aims, it is to find appropriate Lorentz space, LPS. We will give the definition of the Lorentz space later, such that the David-Adams condition, which we for the trace inequality, which we had above, and it reads for the case P is equal Q follows, given by the formula 04 on a measure nu, it is necessary and sufficient simultaneously for this inequality here. For this inequality, we have on the right-hand side the Lorentz norm, on the left-hand side the Lebesgue norm with respect to measure nu. Why this problem? It is interesting. This problem, it is interesting that if we take here in this inequality, the last inequality, S is equal P, then we have on the right-hand side Lebesgue norm, LP norm, and on the left-hand side again LP norm with measure nu. Then the Adams condition, which was given by formula 04, it is not sufficient. So Adams type condition, it is necessary and sufficient in the case when P is less than Q. But in the diagonal case when P is equal Q, this condition is not sufficient. It is necessary but not sufficient. That's why for us it was important to find on the right-hand side of this, on the right-hand side, in the Lorentz scale, in the Lorentz space scale, appropriate Lorentz space with the first parameter P, such that Adams type condition, it is simultaneously necessary and sufficient condition for the trace inequality. Okay? So this was our aim. Even for this inequality which is given here, when P is equal to Q in the diagonal case, Adams condition is not sufficient even for the case when nu it is absolutely continuous. So when d nu it is V of x dx. Okay. So why trace inequality in general it is interesting. For example, by we establish the trace inequality for the risk potential, it is possible to get such type of inequality given by the formula 05 for all f which belongs to C0 infinity, which follows, of course, by the well-known pointwise inequality given by such a formula. Okay, and here in this inequality 05, LQV, it is just a weighted Lebesgue space defined with respect to the following with respect to the following norm. V, it is here weight function. Okay, local integrable almost everywhere positive function. There exists Pfeffer-Funk type but sufficient condition for the trace inequality given by this theorem A, which says that this inequality, so on the right-hand side we have LP norm, on the left-hand side we have weighted LP norm, so this is the diagonal case, but this inequality here, for this inequality, it is sufficient that the following condition 06 holds. So for some R which is greater than P. So this condition 06, it is known as a Pfeffer-Funk type condition, but this condition, it is, as I mentioned, sufficient but not necessary for the trace inequality when P is equal Q. So it is stronger David-Adams condition when P is equal Q in the diagonal case. Okay, so to formulate and in fact, it is easy to see by the Holder inequality the characteristic of V P alpha, where V P alpha, it is just this characteristic given here connected with the David Adams characteristic in the diagonal case. Yes, this characteristic, it is strictly, in fact, strictly less than the characteristic Pfefferman-Fong characteristic here. Okay. Now, to formulate the result which I mentioned involving the Lorentz norm, let's recall the Lorentz. What is the Lorentz space? The Lorentz space, it is this is the in fact this is a Lorentz scale of Lorentz scale which is more precise, let's say, than Lebesgue space. So on this scale, we have also Lebesgue space. So at LPS, it is the space given by such a formula given here. Okay, when S is greater than or equal than S, it is given by such an expression, and when S is equal to infinity, the second parameter, then it is given by this expression. And in particular, when S is equal to P, then LPS space, it is the Lebesgue space LP. So if we denote by F star non-increasing rearrangement on F, then the Lorentz norm also can be written in the following form given by such a formula. Okay, and now the statement, our statement, the main statement of the first part of my talk says the following, that if P is between 1 and infinity, and alpha it is between 0 and n over P, if V is a weight function, then the following statements are equivalent. This trace inequality holds, okay. And the second, that David Adams condition for the diagonal case holds. And also it can be seen that the following estimate of the norm of I alpha by the characteristic of VP alpha holds. The two-sided estimate holds. Okay, so this is the main statement of my talk, the first part. Okay, and this statement was proved in the paper with my PhD student Georgi Merlishvili. It was proved in Georgian Mathematical Journal, but it was announced in some international conferences. And what is I would like to say a few words. So the proof. In fact, this result we found that was obtained also by other authors. I will say about that later, but their approach, it is completely different. Our approach, it is involves the fractional maximal operator M alpha, and first we establish some intermediate statements for M alpha for the trace inequality, and then we pass to the Riesz potential operator. M alpha, fractional maximal operator, it is a very good tool to study, as usual, Riesz potential operator. Okay? Okay. So, the second part of my talk, as I announced initially, it is about the boundedness criteria for fractional integral operators defined with respect to general measure. Okay, we deal with both cases, linear and multilinear settings. Okay, so let me say a few words about the history of non-doubling measure, because we deal with non-doubling measure as usual. Because we deal with general measure. So when a measure satisfies so-called doubling condition, well-known doubling condition, the harmonic analysis it is well developed. For example, singular integrals, fractional integrals, the theory and related topics are very well developed. But when the doubling condition fails for a measure, then of course there difficulties to establish, for example, the boundedness of the operators mentioned by me. So in the beginning of this century, there arisen papers, the appeared papers by well-known mathematicians, which we have on the screen. They studied the boundedness of singular and fractional integrals for in the case of non-doubling measure. Okay. And in fact, the boundedness was established by under so-called mild growth condition on a measure. Okay. So we will discuss. I will discuss now this problem. Generally speaking, for Lorentz spaces, and also generally speaking for multilinear fractional integrals. In particular, we will discuss. We will deliver necessary and sufficient condition on a measure mu, for which multilinear fractional integral operator Tm gamma mu, it is bounded from the product space, Lorentz space, to another Lorentz space defined with respect to measure mu. So this result, which I say for Lorentz spaces, it is also new for the linear fractional integral operator T gamma mu. Okay, so let me now remind you that if we have quasi-metric measure space x d mu, this means that x, it is an abstract set, generally speaking, abstract set. D, it is a quasi-metric defined on x. Under quasi-metric, we mean that the triangle inequality, it is satisfied, holds with some constant. So precise definition will be later. And mu, it is a measure defined on sigma algebra of sets of x. Okay, and this is here given fractional integral operator defined on x. So we see that for the so we have dx mu y. This is a kernel 1 minus gamma. Gamma, it is between 1 and here me I apologize. D mu y should be in the denominator, not in a numerator, not denominator. I apologize for that. Let me, if I manage, I will do this. But you see here, so I have this one. Let me correct. So this should be here. So this d mu y, of course, should be numerator, okay, or outside the fraction. Yes, here. This just misprint. Yes, so this is a fractional integral operator defined on x, which is a generalization of there is potential, which I discussed initially, okay, because we have here dxy, it is a quasi-metric, okay, and just let me pass to the next page. Okay. So, so it remained, so I cannot cut. Okay, so let me continue that J alpha, J gamma, so another operator, this is bilinear fractional integral operator. It was introduced. This is given in Rn. It was introduced by Graf 1992, given by such a formula. This is bilinear fractional integral operator. As a tool to understand that bilinear operator by alpha, such type of operators, fractional integral operators, but written, let me cancel this one, yeah. But given in multilinear form, it is given by calligraphic I alpha. This is F, it is a vector function. Okay, so this integral, fractional integral, was studied as well, and such type of fractional integral operator first appeared in the paper by Koenig and Stein in 1999. Okay. So this is the M-linear fractional integral operator, and analog of this operator, but defined on a quasi-metric measure space xt in mu. It is given by such a formula. D here, as I mentioned here, it is a quasi-metric. Here we have F1 and so on Fm. And so this is the M-linear fractional integral operator given on a quasi-metric measure space xt mu. And so we are interested in the boundedness of this operator, from the product of Lorentz spaces with respect to mu to a Lorentz space with LPQ mu. Okay, so so here it is in correct form written linear fractional integral operator defined on a quasi-metric measure space. Now everything is misprint here is corrected. Here it is this operator here. It is a special case of that multilinear fractional integral operator taking their m is equal 1. Okay, so and in particular we have also the boundedness the criteria for T gamma mu for the linear case. Okay, so we will speak about just for fractional integrals for non-doubling measure. Yes, so there exists in the beginning of this century. It was characterized in the backspaces. The boundedness for such fractional integrals in the papers by the speaker with Kokilashvili in 2001, and separately it was given by Garcia Cuerva Martel, Garcia Cuerva Gatto. They also studied the same problem independently. So, but for the multilinear setting, the problem of characterization of measures ensuring the boundedness of multilinear fractional integral. It was studied by Kokilashvili, Mastillo, and the speaker in 2020. It was published in 2020. Okay, so this is a definition of quasi-metric measure space, which I mentioned already. So why quasi-metric? Because the triangle inequality here, it holds for some constant k. Okay. And now some concepts. So we will assume that all balls on a quasi-metric are measurable. So balls are denoted here by BXR, X with center X and radius R. Okay, and it is assumed that all balls have finite positive measure. And the definition, important definition for us, we say that a measure mu, it is alpha upper beta regular if there is a positive constant B0 such that this inequality here holds for all x from capital X and positive R. Okay, so this is also it is called the growth condition. Okay, so this is let's recall the definition of Lorentz norm, but here Lorentz norm, it is defined with respect to a general measure mu. So this is the in this expression, the first part, it is the case when S is less than 1. So and the second part when the second parameter s is equal infinity. So as before, LP P mu, it just coincides with Lebesgue measure LP mu. Lebesgue measure defined with respect to measure mu. Okay, so it is written here. It is are listed some properties of the Lorentz space, which we discussed above for Lebesgue measure. Okay, so I will not stop here. And now the main results of the second part of my talk. So theorem one. So we have a quasi-metric measure space X d mu. Gamma, it is a parameter over the fractional integral with respect to Martinian fractional integral from so. And if the parameters satisfy the following conditions, okay, and 1 over R, it is the sum, 1 over Rj, 1 over S, it is the sum, 1 over Sj. If we assume that R, it is less than P, and Q, let be another parameter which satisfies this condition that R over P is equal S over Q, then the following inequality here holds, where of course constant C is independent of F1 and so on Fm, holds if and only if mu, it is R force upper beta regular, where beta, it is given by such a formula, by such an expression. Okay, so this is just a necessary and sufficient condition for the inequality 0, 10. And in particular, if we take now Sobolev exponents in the previous theorem, Sobolev, under Sobolev exponent, we mean that 1 over P is equal 1 over R minus gamma, where R it is between 1 and over gamma. Then this inequality, which is a Sobolev inequality for Lorentz space, holds even only if mu is R force upper 1 regular. Okay, so this means that beta here it is R force upper beta regular, where beta it is equal 1. Okay, so and now we as a corollary we can formulate this statement for the linear fractional integral operator defined with respect to mu. So if we let that T gamma mu, it is given by such a formula, which we had already above, then and if R theorem says 3 says that if gamma it is between 1 and 0, R and P are related by this inequality, and S and Q are another parameters, and they are related by this equality here, then this inequality, yes, here is misprint. Here should be on the right-hand side constant C multiplied by the norm of G L R S mu. Yes, so this inequality here holds even only if mu is a upper R force beta regular, where beta satisfies this condition here. So this is also necessary and sufficient condition, and this is just for the linear fractional integral operator, the Sobolev inequality characterization, okay, for this operator T gamma mu, and in particular, this inequality in Lorentz spaces holds even only if mu it is R force upper 1 regular, which means that this condition here holds. So which means so this where B constant B0 it is independent on X and R. Okay, and now we can reformulate this as follows. Now if we are, for example, in Rn, so taking fractional integral operator on Rn, but defined with respect to Borel measure nu. So if we write this in this way, so x minus y with the norm here, it is just Euclidean norm. So we have, in fact, a risk potential operator, but defined with respect to a general measure nu. Then the following theorem holds as a corollary that, which is just the Sobolev inequality for Lorentz spaces, that under this conditions, when P, it is just Sobolev exponent of R, then this inequality here for I alpha, so here should be nu. Here is misprint because we have everywhere nu. Here should be, instead of mu, should be nu. So where I alpha nu G, so this inequality holds even only if nu, measure nu, it is just upper R force n regular. Okay. So in fact, we based on these results, we also got we have appropriate inequality on Lorentz Mori spaces, but I see that my talk will so I will not be in time. Let me just omit this topic and let me start. The sharp estimates for fractional integrals, sharp norm estimates for fractional integrals, and we are concentrated on Olsen's inequality. What is the Olsen inequality? Olsen inequality deals with this type of inequality, 0.13, okay, where we have on the left-hand side, we have the bilinear form. In fact, this is a bilinear inequality. I alpha, it is the risk potential of F, and constant, it does not depend on G and F. And these norms here, E norm in E, F, and X, they are in fact Mori norms. They are Mori spaces. Okay, so this is this type of inequality. It is called Olsen inequality, and such type of inequality first appeared, and also application is a paper by Olsen in 95. Okay, and then later it was studied by Japanese mathematicians, for example, by Savano and his collaborators as well. Okay, and what was our aim? Our aim was the following, that to establish this type of inequality generally speaking, in the multilinear form where I alpha it is multilinear fractional integral. And another our aim here was that to establish sharp Olsen inequality, which before was not known. And what we mean under the sharpness? Under the sharpness, we mean that here the norm of G in appropriate Mori space E, it is such that we cannot replace this by the smaller norm in Mori space again. Because before such type inequalities were established, but above the sharpness, nothing was said before. Okay, so we mean this optimal form of the Olsen inequality. Okay, so as I mentioned, such type of inequality appeared first by Olsen when he studied on the ball in R3 the following equation. Okay, so and now for us was interested to establish in the multilinear setting, generally speaking, but the result it is also new for the linear case. So in the multilinear case, that Olsen inequality can be understood in the following form. So this is the first inequality here, where I alpha it is multilinear fractional integral. Okay. And why this inequality is also interesting? Because if we establish the sharp form this inequality, it gives, in fact, trace inequality criteria in spaces for the operator I alpha. So they are connected to each other. The sharp form of the Olsen inequality, it is connected with the trace inequality characterization in Mori spaces. Okay. So, and we have also the characterization of the following trace inequality given here for the bilinear fractional integral operator. Okay, so I would like to say, because we mentioned also weighted inequalities for multilinear fractional integrals, and it was studied, for example, one weight characterization by Moen, and also by him was also established power bump, two weight conditions, but the trace inequality characterization in Lebesgue spaces for multilinear operators, multilinear fractional integrals, it was given by the speaker jointly with Mastilo and Kokilashvili in 1914. Okay, so what about the Mori norm? Mori space, like the Lorentz space, depends on two parameters. So for us, it is convenient to have this notation here in this form, because it has several equivalent notation of the norm. For us, it is convenient now to have this form. So this is defined the Mori norm here with respect to a general measure mu. Yes. So LQR, the norm, where f it is locally integrable function on Rn, mu it is a Borel measure on Rn, and this is the norm. We say that f belongs to this space LQR if the following supremum it is finite, where supremum it is taken over all cubes with sides parallel to coordinate axis, bounded cubes, of course. So if this supremum it is finite, then we say that f belongs to LQR d mu. When d mu it is locally integrable, which means that d mu it is v dx, where v it is capital V, it is just weighted function. Yes, then we denote this space by LQRV. V in this case, it is written in brackets here. Okay, so there are known in Mori spaces Sobolev type inequality in two different forms: Spanner's result and Adams result. So, and under this, for example, the proposition A, this is a Spanner's result. It is formulated for this definition of Mori space if P0, S0, Q0, R0 are related by these conditions here, then the fractional potential operator, it is bounded from one Mori space into another, and here is given a David Adams theorem. So under this condition on parameters, now I alpha is bounded from this Mori space into another one, and it is known also in multilinear setting also Sobolev type inequality, which is given here, yes, under these conditions on parameters, the following inequality for multilinear fractional integral I alpha holds. Okay, and now, yes, this is the David Adams trace inequality, which I formulated for Lebesgue spaces initially on my talk. Again, let's recall this characterization, but this characterization is true when P is strictly less than Q. Okay, for Lebesgue spaces. Okay, so this is just which we formulated above. And now let me formulate the trace inequality characterization for multilinear fractional integral operator I alpha. This was published in 2014 by the speaker jointly with Kokilashvili and Mastilo. Okay, when pi satisfies this condition here, and alpha it is between n over p and 0, p is less than q. Here, p, it is defined as follows, that 1 over p, it is the sum of 1 over pi. Yes. Then the following inequality holds if and only if this David Adams condition on V it is satisfied. Okay, and now the main result for measure the main result for the sharp Olsen inequality. So so we assume that parameters which conditions which are listed here are satisfied. Okay, then the following Olsen inequality is satisfied, and also this inequality sharp because here G, the norm of G in LQL norm here cannot be replaced by the smaller norm again in Mori space. Okay, again we cannot replace by the smaller Mori norm of G. Okay. And as I mentioned, from this sharpness and from this inequality and from the fact that this inequality is sharp in this sense, just I mentioned, we have the trace inequality characterization for the multilinear I alpha, and in particular, this inequality here holds if and only if weight V satisfies the following David Adams type condition. Okay, so for multilinear I alpha in Mori spaces, we have this characterization in Mori spaces. As a corollary, of course, we have this is the Olsen inequality of the linear. For the linear fractional integral, we have this sharp inequality here given under these conditions on parameters of Mori spaces. I alpha here is the risk potential operator. Okay, and here are given some bilinear inequalities as well for by alpha. For the bilinear operator by alpha, I defined this operator above. So and we have the following Olsen type inequality as well. Okay, and this is a trace inequality for by alpha, David Adams type. In fact, here it is again also an inequality because it is written here characteristic of mu in this inequality. Okay. And here it is in the Lebesgue spaces, the similar inequality. Okay, and now since I don't have much time, I will pass. I will come back to the first part where I discuss the trace inequality for fractional integrals in the multilinear setting, and I deal with now for one-sided fractional integral operators. Okay. So let's consider the following multi-M-linear Riemann-Liouville operator given by such a formula here. We see that this is the Riemann, when M is equal 1, this is just the classical Riemann-Liouville operator defined on 0 plus infinity, and our aim to give a characterization of this inequality given by the formula 0.22 for this operator, a multilinear one-sided operator here. We have on the left-hand side the norm of R alpha from the vector function f, and weighted norm on the left-hand side. On the right-hand side, we have the Lebesgue norm LPK, okay, product of the weighted norm. Okay, so when we take here alpha is equal m, okay, then we have the multilinear Hardy operator And the two-weight criteria for such an operator is well known. For example, for H2, by these authors were established in 2012 and also independently two-weight criteria necessary and sufficient condition for HM. The hard inequality, of course, has a long history, and of course, it will not be enough half an hour to discuss this history about hard inequality two-weight history for the hard operator. That's why I just mentioned only a multilinear setting about that. So when we take in M linear operator, M is equal 1, as I mentioned, we have a Riemann-Liouville operator with parameter alpha, classical Riemann-Liouville operator. And for the two-weight for the classical Riemann-Liouville operator, for when alpha is greater than 1, in this case, we don't have singularity here. It is well known, for example, it was established in 80s of the last century by Stepanov without singularity. But when we have singularity, then two-weight criteria, it is also well known. But for the Riemann-Liouville operator defined on the whole real line of this form, minus infinity here, sorry, here should be minus infinity to x in this definition for this operator. It is well known. There exists different type, for example, Sawyer type characterization for this operator given by Lorente, and there exists Gabizashvili-Kokulashvili type characterization for such operator. But when we deal with the operator zero infinity, I mean zero infinity, yes, for this case, the two-weight problem, as far as I know, it is not known. I mean that good condition, but there was characterization, I mean trace inequality characterization established by the speaker in 98 and independently by Prokhorov in 2001. It is well delivered, this history about this in the monograph by Edmund Skokulashvili and speaker published in 2002. And let's come back to our multilinear fractional integrals. So this is the M linear. So that Riemann-Liouville operator M linear can be rewritten also in this form. Okay, it is in fact one-sided version of this multilinear fractional integral operator of RIS type, which I discussed. Okay, so our alpha operator, in fact, was introduced and studied by these authors here in 2015, and now our result about the operator I alpha, R alpha, multilinear fractional integral, one-sided fractional integral operator, reads as follows: that if we assume that we have parameters P1 and so on, PM, and Q, which are related by this condition, alpha it is greater than this this number here, we are for some I0 it is between 1 and m, where P prime I0 it is just conjugate number P I0, then the following statements are equivalent, that this multilinear trace inequality holds here for L alpha, and this condition 2, simple condition 2, it is satisfied for weight function V, and then it is equivalent, on the other hand, to the following dyadic type condition on weight function V. Okay, and also we studied the similar problem, similar characterization for the following Riemann-Liouville, M linear Riemann-Liouville operator, given here we have the product of one-dimensional Riemann-Liouville operators like this. This is also M linear here, and this calligraphic R alpha can be understood as a generalization of also of m-linear Hardy operator, taking here alpha k is equal 1. Okay, we can understood, and we have the similar characterization of the trace inequality for this calligraphic R alpha. In particular, we have now under these conditions here, which we have here, the following statements are equivalent. Okay, characterization of the inequality 1. Okay, and in fact, when m is equal 1, both these statements which I formulate gives us a trace inequality characterization established by the speaker, which and Prohorov independently given 25 years ago. So and we have here. So this is also, it should be underlined that here this characterization involves the diagonal case when P is equal Q. Okay, now regarding them, so I already finished, but I will say I have a few minutes. I will say show you the references. So about here are listed classical papers about the trace inequality, the history for risk potentials. Okay, the papers by David Adams, Herman Sawyer, Magia, Verbitsky. Yes, so where the history of the trace inequality for risk potentials are very here are given monographs, for example, for trace inequality for one-sided fractional integrals or multiple fractional integrals. I mean that fractional integrals with product kernels also in these monographs. So here are given the recent results, our and also of other authors regarding the topics which I discussed. And I would like to mention that I forgot that Sharp-Olsen inequality was established by the speaker jointly with Lucas Grafakos. It was published it was published last year in journal of potential analysis. I forgot about that. And the last part, I mean the part of trace inequality for one-sided potentials was published by the speaker jointly with David Edmunds and my PhD student Natela Shvili. Okay, here are given also some other criteria, for example, for characterization of measure mu, for which fractional integral operator with respect to mu is bounded. It was published in Lorentz spaces. It was published in 2000 in this year in this paper here, the first paper on the screen. Okay, but in Lebesgue spaces, it was studied in 2001 by the speaker jointly with Kokilashvili, and independently it was published by Garcia Cuerva in Studia Mathematica. It was okay. So, and other relevant papers also about this topic. Okay. So some multilinear, so the papers about multilinear operators, okay, two-weight, one-weight characterizations and two-weight results, okay, so are given here. Some also monographs, also one-sided Riemann-Liouville operators, the boundedness problems. Okay, and so that's all. I exaggerated, I think, for some minutes, but so this is then my talk. Thank you very much for your attention.
Thank you very much for the interesting talk. Do we have any questions from the audience or comments? I am, in fact, curious about these multi-dimensional operators. Some of them I have seen before, maybe some of them not.
You mean multilinear?
The Riesz potential, is
Riesz
that the
potential.
one that is the inverse of the fractional Laplacian operator, or is it something else?
Riesz, sorry, can you repeat the question? So we consider here, I considered classical Riesz potential operator, okay, and as well as its multilinear version. What do you mean? Which one?
I'm just trying to remember the classical Riesz potential. Is
Yes,
that
yes,
the
yes.
inverse of the fractional Laplacian operator?
Yeah. A fractional Laplacian operator. Yes, okay, it is connected, of course.
Yeah.
Of course, yes. Yes.
And your multilinear operator, does that relate with the multi-dimensional Riemann-Liouville integral, as in the operator you get simply by applying Riemann-Liouville in each dimension, or is it totally separate?
Yes, but I don't know. I never thought about in this direction. No, no, I don't know. Maybe it is also related. I know, for example, that multilinear fractional integrals are connected with Onge inequalities, type inequalities. For example, in the surveys of Grafakos, I have seen such types, but I don't know more with Laplacians how it can be applied. I don't know
Okay. Okay,
with
thank you.
multilinear setting. It is a good question, but unfortunately, I don't know.
Okay, thank you. Any other questions, comments from anyone else? If not, then we thank the speaker again. I will stop the
Thank you
recording.
very much. Thank you.